On the theory of strange stars, many researchers are now engaged. However, many of these characteristics are still poorly understood. For instance, it is unclear how quark matter behaves when the pressure is decreased or whether neutron matter transforms into quark matter in a reversible manner. Here, two opposing theories are put forth. Either a weird substance created in the core of a neutron star will keep its qualities even at low pressure, or a reduction in pressure and density will cause quarks to merge into neutrons. Another concern is whether the quark star will be made entirely of quark matter or if the quark core can be surrounded by a crust of neutron or conventional matter, which could be rather thick. Since many of the observational characteristics and manifestations of such stars are quite similar, it becomes exceedingly challenging to distinguish it from a neutron star in the latter scenario, but efforts are being made in this direction. It is extremely hot inside the compact supernova remnant that was left over after the explosion, billions of degrees. The radiation from electromagnetic waves and neutrinos lowers its temperature. Quark and neutron stars cool in various ways. A neutron star loses thermal energy mostly during the first 100,000 years of its existence by the emission of neutrino pairs, which are created in the star core during repeated processes involving the emission and capture of electrons by neutrons. A quark star must also emit neutrinos, but the main active particles are quarks in this case. Quark stars will cool far more quickly than neutron stars, according to calculations based on the current models. The two stars may be virtually identical in terms of mass, radius, and surface thermal radiation if the quark core is covered in a crust similar to that of a neutron star. The detected objects might theoretically be arranged on the H-temperature diagram to discriminate between these two classes of stars, as quark stars, even those with a shell, should appear to cool more quickly than neutron ones. It should be noted that a number of little understood variables affect how stars cool, including the processes permitted in neutron stars, whether or not material inside them transitions into a superfluid state, the chemical composition of the atmosphere they are covered with, and the strength of their magnetic fields. These variables for quark stars include also the time at which neutron matter transitions into quark matter and the quantity of energy emitted or absorbed during this process. The opposing dependency of their radius on mass is another obvious distinction between neutron and quark stars' characteristics. Compared to regular neutron stars, quark stars have a distinct equation of state. Smaller radii for the same mass of a compact atom are one way this shows up. So it is feasible to ascertain the nature of an object by measuring its mass and radius. The most massive neutron stars are the smallest because when a neutron star's mass reduces, its radius increases. The smallest neutron star's radius is 10 to 12 kilometers at the most. The link between size and mass in quark stars is linear. The heaviest quark stars are the largest, and low-mass stars are very small. This discrepancy is of little use to observers since the neutron stars' masses, for those for which precise measurements have been made, fall within a relatively small range of 1.35 to 1.41 solar masses, where the radius essentially remains constant. Therefore, we can assume that the object you are witnessing is a quark star rather than a neutron star if you see a neutron star whose surface temperature is noticeably lower than the expected age, or if its radius turns out to be noticeably less than 10 kilometers. However, you must first confirm repeatedly the accuracy of the calculated numbers for the object's age, radius, and temperature. As was already established, it is quite challenging to discern between a neutron star and a quark star that has a crust of ordinary matter. Some scientists think that practically all known neutron stars are actually made of quarks. Others, however, do not go that far. It is thought that there are qualified candidates who need more examination. Another intriguing theory put forth by Polish researchers can be utilized to distinguish neutron from quark stars. This is due to the fact that when they create a binary star system, they behave differently. The Milky Way Galaxy contains binary systems, which are pairs of stars that orbit one another. There are few instances that we are aware of where two pulsars are not far apart from one another. Strong interactions between the stars in these tight systems lead to internal oscillations. As it turns out, quark stars' radial oscillations differ significantly from neutron stars. In the case of the latter, their energy steadily vanishes without changing how the binary system evolves. For quark stars, the opposite is true. The energy of the oscillation instantly radiates away, greatly affecting the system's evolution. The structure of the star directly affects how quickly a quark star's oscillations lose energy. The density of strange quark matter, 10 to 14 grams per cubic centimeter, is identical to the density of mass on the surface of a quark star, where pressure is no longer an issue. A neutron star's surface is completely different. It is composed of iron atoms that form a crystal, just like pure iron on Earth, which has a density of 8 grams per cubic centimeter. A star's radial oscillations can be essentially characterized as cyclic shrinking and growing. These oscillations often have a very tiny amplitude. The amplitude, however, may be as high as several dozen percent in exceptional circumstances. The radius of the star expands during the process, leading to a rise in volume and a decrease in density. That entails a neutron star's iron slightly expanding, then slightly contracting, and so on. Over time, these oscillations lessen. The scenario is entirely different in the case of a quark matter star. Quark matter enters an excited state, which transforms it into an entirely distinct type of matter, when its density falls by 0.3%. Over the course of the first cycle, all of the oscillation energy is converted into latent heat, and the oscillations vanish. It literally means that a quark star's energy dissipates right away. It used to be believed that neutron stars and quark stars and binary systems looked exactly the same as one another as they approached one another until they eventually formed a black hole. However, if we take into account this energy dissipation mechanism in quark stars, the history of both types of stellar systems will turn out to be very distinct.